So in here, we are to cool down our fish. And there is a change in temperature above and below freezing, and there's also an involved latent heat. So this is a combination of sensible heat and latent heat. So that is our solution for this problem. So for the capacity for the total load, that will be equivalent to mass, which is 11,000 kilogram. And the whole process is on a span of 11 hours. Multiplying this by 3,600 to make this seconds. Let's start with our sensible heat above freezing. So our CP above freezing is 0.7. And our change of temperature above freezing, so initially we are at 20, then minus the freezing point, which is -3, plus our latent heat of freezing 55.5, plus our sensible heat below freezing, that is 0.3, times our change of temperature. So initially we are at the freezing point, then our final state is negative 10. That will be minus negative. The unit inside is kilocalorie per kilogram. Cancel out kilogram. So you can see the remaining unit is kilocalorie per second. But we are asked here to find the capacity in tons of refrigeration. So first, let's convert kilocalorie into kilojoules. So in 1 kcal, there are 4.187 kilojoules. And then now we have kilojoules per second or kilowatts. And we know that in 1 ton of refrigeration, there are 3.5167 kilowatts. What is our capacity of the plant in tons of refrigeration? This is equivalent to 24.37 tons. In a PD diagram of a pure substance, the curve separating the solid phase from the liquid phase is the fusion curve. How much refrigeration capacity is required to cool 2,000 cubic feet per minute of air from 85 to 70 degrees Fahrenheit? So again, we're asked about the capacity. And as we can see, there is a change in the temperature of the air from 85 to 70, meaning the capacity can be solved using the sensible heat formula, which is mCp delta T. So M is the mass, Cp is the specific heat at constant pressure for air, and delta T is a change of the temperature. Cp is a constant, while delta T is a given. But we don't have here a mass, because what we do have here is 2,000 cubic feet per minute, or that is the volume flow rate. But we all know that the mass is also equivalent to the density times the volume. So let's use that. Okay? So mass equivalent to the density of the air times the volume flow rate of the air. So take note, the rho for the air is 0.075 pounds per cubic feet in English unit. And the volume is 2,000 cubic feet per minute. So in that case, the unit of mass is pounds per minute. The Cp of air is 0.24 BTU per pound runtime, and our change of temperature is 85 minus 70. Take note, the change in Fahrenheit is also the change in runtime, and pounds is also cancelled. So the remaining unit here is BTU per minute. But we are asked here to find the capacity in tons of refrigeration, as you can see from the choices. So from BTU per minute, we must convert that into tons of refrigeration. So for the conversion factor, 1 ton of refrigeration is 200 BTU per minute. What is our refrigeration capacity? The answer is 2.7 tons of refrigeration. Form of energy associated with the kinetic energy of the random motion of large number of molecules. Heat. So let's analyze first the problem. So what we have here, we started at a temperature of 29 and we ended with 2 degrees Celsius. So there's a change of temperature. And further reading the problem reveals that there is no changes in the phase that are mentioned in the problem. So meaning we are only cooling down the milk from a certain initial temperature to a certain final temperature without changing its phase. Meaning our load is sensible heat. Okay, so this will be mCp delta T. So our M is the mass, but what we do have here is the volume, which is 20,000 liters. To make that mass, we must multiply that with the density. And what we have here is the Sg. So we know that the density of the milk will be equivalent to the specific gravity of the milk, 1.05 times the density of water, which is 1 kilogram per liter. So that is our density, multiplied by the volume of the milk, that is 20,000 liters. And that is within 5 hours. So 5 multiplied by 3,600 to make that seconds. So that is our mass flow rate of the milk, multiplied by the specific heat of our milk, which is 3.9 kilojoules per kilogram Kelvin. And then our change of temperature, we started from 29 and we ended with 2 degrees Celsius. So that is our ideal cooling load. Ideal meaning there are no losses. But in this case, refrigeration losses amount to 10% of the cooling load. So if there are losses in the system, we must compensate that with more energy. So in that case, we will be multiplying the sensible heat by 1 plus the percentage of losses. So that will be 1 plus 0.10 or 1.10. So the remaining unit is in kilojoules per second or kilowatts. But the choices are expressed in tons of refrigeration. So we should convert that. So we know that per 1 ton of refrigeration, there are 3.5167 kilowatts. What is our capacity of the refrigerating machine? This is equivalent to 38.43 tons of refrigeration. Best answer, 38.5. A Francis turbine has what flow? Inward flow reaction. How many tons of refrigeration are required to produce 10 metric tons of ice per day at negative 10 degrees Celsius from raw water at 20 degrees Celsius if miscellaneous losses are 15% of the chilling and the freezing load? So we are asked here to find the load in tons of refrigeration in producing ice from negative 10 degrees Celsius from water at 20 degrees Celsius. So this involves sensible and latent heat. So for our load, that is equivalent to the mass, which is 10 metric tons, and we know that 1 metric ton is 1,000. So that is also 10,000 kilogram. That is per day. So we know that per day there are 24 hours, and per hour there are 3,600 seconds. That's our mass. So let's start with our sensible heat of the water. So that will be Cp of water, 4.187, times the change of temperature of water. So we started at 22, then minus the freezing point of the water, which is 0, plus the latent heat of fusion, which is 335, plus the sensible heat of ice. So that would be Cp of ice, which is also the 1/2 of the Cp of water, that's 2.0935, times the change of temperature of our ice. So we started at the freezing point minus the final point, which is negative 10 degrees Celsius. So the unit inside is kilojoules per cell. So that's our ideal load. But in this case, we have miscellaneous losses. So we'll be multiplying the whole term by 1 plus 0.15 or 1.15. That would be kilojoules per second or kilowatts, but the choices are in tons of refrigeration. So let's convert that. So we know that in 1 ton of refrigeration, there are 3.5167 kilowatts. What is our answer? The answer is 16.96 tons of refrigeration, or most nearly equal to 70. The condition of pressure and temperature at which liquid and its vapor are indistinguishable. Okay, so in this case, we are required to find the pressure at a higher elevation of 12,000 feet. So we know that as we go higher into our atmosphere, the pressure decreases, and if the air is incompressible, so the density of our air is constant at any elevation. So in that case, we could solve our pressure at any elevation by using the formula P2, the pressure at any elevation, is equal to P1, the pressure at the sea level, minus rho GH, where rho is our air density, G is the gravitational acceleration, and H is our elevation. Okay, so P2 is equal to P1, and that's 14.7 pound force per square inches, minus rho, so that is 0.0763 pound mass per cubic feet. G is 32.2 feet per second squared, and our H is 12,000 feet. So obviously, our final answer should be in PSIA, or pound force per square inches. So we must manipulate our units. As you can see here, our numerator should be in pound force. But in our solution, in our rho GH, there is a term pound mass. So take note, pound force and pound mass are different, because pound force is a unit of force and pound mass is a unit of mass. So there must be some conversion factor. And that is equivalent to 1 pound force is equal to 32.2 pound mass feet per second squared. You can cancel out pound mass as well as feet per second squared. And we can cancel out one of the feet. So our remaining unit is pound force per square foot. And our remaining process here is to convert square foot into square inches. So we know that 1 square foot is equivalent to 144 square inches. What is our final pressure at 12,000 feet elevation if air is taken as incompressible? The answer is 8.342 pound force per square inches absolute. Heat transfer due to density differential is convection.